Alright, Chapter 6, Part 2. The first part of this is we're going to talk about Lewis structures. The second part we're going to talk about Vesper's theory and molecular geometry. In molecular structure, as far as molecular structure goes, we want to talk about Lewis diagrams. How to get to these shapes of these molecules. You remember we did Lewis dot diagrams at the end of the last chapter, and I kind of showed you how the electrons move and how they pair up. Now we're going to use Lewis diagrams to predict the shapes of structures. Now if you need to have a little bit of a refresher, you may want to go back and see how these compounds are formed. But it's all based around the octet rule. Alright, remember, most atoms form bonds in order to have 8 electrons in their valence shell. Now, I've been telling you this, but I have not told you the exceptions. There are several exceptions to the octet rule. The first of which being hydrogen. Remember, hydrogen only wants 2 electrons in its valence shell, and you should remember from the last example, or the last lecture I gave, we were talking about how the hydrogen only wants 2. That's how it pairs up nice with water. Now, here's another exception. Groups 1, 2, and 3 get 2, 4, and 6 valence electrons respectively. So group 1 wants 2 valence electrons. Group 2 wants 4 valence electrons. Group 3 wants 6 valence electrons. Not that confusing. I'm going to show you with an example of boron. Boron is in group 6 on the periodic table. And it has it's in group 3 on the periodic table, and it wants 1, 2, 3, 4, 5, 6 electrons in its valence shell. Remember, fluorine is not in that group. It still wants to have 8, and if you look at each of the 8 around here, each of them have 8. Now, there's something called an expanded octet, where usually a metal, transition metal, will hold more than 8 valence electrons. The best example of that is sulfur hexafluoride. Sulfur will actually hold 12 valence electrons in its outer shell. And there are a few radicals which we will not deal with in regular chemistry 1, but I do want you to be aware of them for when you get to college. Examples like NO. This variation of NO is very unstable. Notice that the nitrogen has 1, 2, 3, 4, 5, 6, 7 valence in its outer shell, very unstable. So those odd numbers of electrons. So let's talk about drawing Lewis diagrams. We have several rules we need to talk about. The first one is to find the total number of valence electrons. How do we determine the number of valence electrons? Well, we look at the element's position on the periodic table depending on which group it's in. 1, 2, 13, 14, 15, 16, 17 tells us how many valence electrons we have. Then we must arrange the atoms in a logical sense. The singular atom, or the one that's by itself, is usually in the middle. Or the most electronegative atom is usually going to be in the middle. Usually. Now, we form bonds between atoms. Each bond we represent with a line, and that line represents 2 electrons that are being shared. Then we distribute the remaining electrons to give each atom an octet, with the exception of a few oddities. Okay, so let's actually put this in. If there aren't enough electrons to go around, we must form double or triple bonds. We must always remember that everything wants to have wants to be happy with an octet. Let's look at carbon tetrafluoride, CF4. Alright, the first thing we need to do is we need to determine the number of valence electrons. Carbon has 4 valence electrons. It's in group 14. We should remember that group 14 has 4 valence electrons. We have 1 carbon atom, so we have 4 valence electrons. We have 4 fluorine atoms. If you remember, fluorine is in group 17, so fluorine has 7 valence electrons. Then we add these two together and get a total of 32 valence electrons. Now, let's arrange our atoms. Remember, the singular atom is going to be at the center, surrounded by the other atoms. Alright? Now, the carbon is going to bond with each of the fluorines. So we have 2 electrons here. Remember, each bond's worth 2 electrons. 2, 4, 6, 8. So that means that the carbon is happy. Carbon is sharing 8 electrons with each of these 4 fluorines. So carbon's happy. Its octet has been met. Now, 2, 4, 6. We have used 8 of our electrons, so let's subtract that from our total. We have 24 left. We distribute the rest of those 24 around the fluorines until it's happy. Alright, each fluorine will get 6 electrons, giving it 1, 2, 3, 4, 5, 6, 7, 8. Remember, bonds count as twice. So each of the fluorines are happy with an octet. So this is just a standard octet rule. No exceptions, no frills, no interesting things. Beryllium chloride. Beryllium chloride is a little bit different. Remember, beryllium is an exception. It's in group 2, so it only has to have 4 valence electrons. Alright, so let's determine the number, or it's happy with 4 valence electrons. Let's determine the number of valence electrons. Beryllium is in group 2, so it has 2 valence electrons. And chlorine is in group 17, so it has 7 valence electrons. We have 2 of them from our formula. So we end up with 14. We end up with 16 electrons total. Now let's draw our diagram, or arrange our atoms rather. Remember, the singular atom is in the middle, and they're going to be bonded together. Now beryllium is happy. It has 1, 2, 3, 4 electrons, sharing 2 or 1 with each of the chlorines for a total of 2 shared. So we have 4 electrons with beryllium. 1, 2, 3, 4. It's happy. Let's subtract that from our electron total. 4 electrons, get those from the bonds. We end up with 12. Those 12 need to be distributed around the chlorines to make them happy. Remember, beryllium is an exception. Everything is happy here. The chlorines have 1, 2, 3, 4, 5, 6. Remember, the bonds count as 2, 7, 8. 8 valence electrons. We have octets on either chlorine, and the beryllium is happy. Carbon dioxide, CO2. Remember, carbon is in group 14, so it has 4 valence electrons. We have 2 oxygen atoms. Oxygen is in group 16, so we have 6 valence electrons for a total of 12. We add those valence electrons up. We end up with 16 valence electrons. All right. We arrange our atoms with the singular atom being in the center, and we're going to bond those 2 atoms. So we've got 1, 2, 3, 4. So we have 12 left. Okay? Now, we're going to put dots around each one of these, or we're going to put the remaining dots around each one of the oxygens. Okay? So the oxygens, let's see how many they have in their valence. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So the oxygens are happy in their valence electrons. However, the carbon is not. Carbon has 1, 2, 3, 4 in its valence. Carbon follows the original octet rule, so it wants to have 8. How do we make it have 8? Well, we share these 2 electrons. See where they come from? We share these electrons with carbon, and we form double bonds. So now let's look and see if everybody's octet is happy. We have 1, 2, 3, 4, 5, 6, 7, 8. So each of the oxygens are happy. And then carbon, 1, 2, 3, 4, 5, 6, 7, 8. And the carbon is now happy. I know that's a little more confusing, but we'll work with it in class. Okay? Polyatomic ions. Remember, polyatomic ions mean we have more than one ion in a compound. So we must find the number of valence electrons. Remember, they're charged, so they may have a little bit different number of valence electrons. To find the number of valence electrons, we add an electron for each negative charge, and we subtract an electron for each positive charge. And we place brackets around the ion and label that charge. So let's look at an anion, or a negatively charged polyatomic ion. ClO4 minus. Alright, chlorine's in group 17. We end up with 7 valence electrons. We have 4 oxygens. Oxygen's in group 16. We end up with 6 electrons. 7 plus 24 gives you 31. Now, we have to account for this charge. We took on an additional electron, so we have 1 more electron. So we end up with a total of 32 electrons. We arrange our atom with the singular atom being in the middle, and we form bonds. 1, 2, 3, 4 bonds with the chlorine. So this is 2, 4, 6, 8. Electrons around the chlorine. The chlorine is happy. We subtract that 8 from that 32. We end up with 24. Now remember, we distribute the remaining electrons around the oxygens so that they're all happy with an octet. 1, 2, 3, 4, 5, 6. And remember, bonds would be 7 and 8. And we need to indicate the charge by placing brackets and the charge outside of the brackets. And a positive ion, a polyatomic ion, or a cation. Let's look at ammonium, NH4 plus. Nitrogen has 5 valence electrons. It's in group 15. Hydrogen is in group 1. Remember, hydrogen is an exception. It has 1 valence electron, and it's happy with 2. Okay, so we end up with 9 valence electrons, but we have a positive charge. Remember, if we have a positive charge, we actually took a negative piece away from it to make it positive, so we subtract a negative piece. We end up with 8 valence electrons. We arrange the nitrogen in the middle, because it's the singular atom, around the hydrogens. We form bonds, so that's 2, 4, 6, 8. 8 valence electrons, that's all we need. Remember, hydrogen's happy with just 2. And we have to put our polyatomic in brackets with the charge. And that is it for drawing Lewis structure. We will use these to predict the molecular geometry in the next section.